All right, but let's get into then what we had last time. So, and we'll actually have some code today, so that way we don't have to like look at a bunch of stuff, like just conceptual. So just to kind of review a little bit, we talked about statistical testing last time. We talked about the t-test, right, and saying like you shouldn't really use a z-test, like there's no reason to it. There's too many assumptions that you're okay, use a t-test. And in fact, the t-test that we were showing was actually the student's t-test. And we'll talk about that with the students versus Welch's test today. But quick thing is that we talked about types of errors. So we'll actually revisit this maybe like when we talk about Bayesian statistics, because that'll be really important. So types of errors, if you are looking to say, hey, like out of this whole thing, like what are we going to see the most about and like really should understand about it? I would probably say type of errors is common throughout all of statistical learning, machine learning. Is that knowing what kind of errors we make. Actually, this is great. I actually had this example like literally after class yesterday. I was talking with Emily's cousin, who I don't think they'll mind me sharing this or anything, but they're also pregnant, and she was saying they were testing, I can't remember the exact numbers, but basically like the spinal fluid gap, like they're like early days kind of stuff, and they're basically testing like, oh, like if you have a larger gap, essentially, there's a higher chance of what's it called? Of like Down syndrome and other possible issues and stuff like this. Like I shouldn't say issues, but like other things they have to look out for. So when they did the numbers, they did it through there, and they're like, oh, like the numbers are higher than it should be or whatever this threshold. And so they sent through and they did a test. Well, like they went to a genetic counselor to like kind of talk about like what's going on, like what are these options, what is all this stuff. And when I said the number, I can't remember the exact numbers. Like I was like, oh, it was like 3.5 or 3.4 millimeters, or whatever that means. It means nothing to us, right? Just a relatively low number. And the genetic counselor says, oh, like you guys are like honestly, you guys are probably fine. Like there probably isn't issue in here. And the genetic counselor was explaining at least is that at least in California, they had recently lowered the threshold from a higher number to a smaller number where they would actually have to get talk with a genetic counselor, get an additional blood work test, which is more reliable and saying like, specifically for like, like say for Down syndrome and stuff like that. And they basically said like they lowered it down. And so like usually they said like usually basically most people in this range probably are going to be fine. And so it was kind of interesting because it's like that is exactly what, and for the record, they did do the blood test and they were negative, like the baby was negative for the things that they were testing for. And so it was good news for, for the parents and stuff like that. But, it did cause them a little bit of anxiety, a little bit of like concern and stuff like that. But it was in fact like a type 2 error, right? It was significant. It was tested as, oh, it's significant or not significant. We said, oh, it's you're positive. Essentially, that's what that test was, right? And then following up the second test is like, oh, you actually are negative. So you truly are negative, even though you're positive. So you can also see like how different errors can give different like, what's it called? Like have drawbacks and stuff like that. So that's something to kind of consider like when you're talking about type 1 errors and type 2 errors, especially when you start doing more into predictive analysis, like machine learning, stuff like that. So you talk about like deep learning with face recognition and stuff like that. You have to really think about like what kind of errors can it make and what error are we going to be more okay with essentially, or like, is it okay to make more of these errors to make this type of error go down? So in this case, in California, whether you agree with it or not, lower this number to say, okay, we're gonna get more false positives, right? But, we find that, the reasoning at least behind it would be that, oh, it's worth getting more false positives than getting more false negatives. And so that's kind of like the calculus essentially of what someone was kind of going through, or policymakers, whoever made the decision. Okay. So anyway, I thought I was like, oh, perfect time. I can talk about this. So anyway, type errors, something that will come up again for sure. And I would say go through it, really understand what type 1 error versus type 2 error. Effect size, we talked about effect size. We saw the ANOVA and stuff like that. Important to know basically what is the difference. It's different from actual significance. And then we talked about statistical power, where statistical power basically helps us determine, how many samples we should do, what kind of tests we do. And we should calculate these things beforehand, in an ideal world, versus like trying to modify what we've done. If you get, let's say you do some tests and like you find you're not in the significant, it wasn't statistically significant, but you feel that there's an inkling, like it seems like this would be significant, you shouldn't just simply modify your test to make it like double check. You need to really, like good practice is really to redo the test with new samples, right? Not just basically modify a test that you have, whether that means bring a couple new samples in there or change your significance level or whatnot. Okay, cool. All right, so this brings us today, which we have about 10 minutes, but I'll be fine, is Welch's t-tests. So we didn't even talk about Welch's t-test last time, right? Okay, I see head shakes, good. So I won't kind of review, I'll quickly review. Just remember t-test is actually from the curriculum. Basically, we are taking, we get our t-statistic, right? And that's gonna be actually determined from the t-distribution. So we say, okay, here's our sample, we calculate our statistic. Note that when we say statistic, what we're saying is it's from some sample, it's from some data. A statistic, I almost think of it like it's some summary of like the data in some form or fashion. So this t-statistic is describing of that sample. And then we take this and basically compare this with what our expected part is. And we compare that with their significance level, which is alpha, or, you know, if you convert it into T star. You guys, I don't think you guys see that in the curriculum. Just real quick, because I've mentioned a few times. Usually you see like T statistic, or sorry, T critical value, but you also see something like T star, like with a little asterisk above. Note that those are the same thing. So in some texts or some academic papers, you'll see T star. That means the T critical value. Okay. So we have our part and we compare it and say, okay, if our T critical value is less than or more than our T statistic is greater than our T critical value or T star, then we say, oh, we reject the null hypothesis, right? Otherwise, we fail to reject it. Okay, right? I think this is pretty simple. And what's nice is that if you think of it in those terms, it doesn't matter what test you do. It's just like, oh, you get your blank statistic, your F statistic, for example, and you say, okay, is it more than our critical statistic, you know, whatever that is, and say, okay, then we reject it. Or you can take your test statistic and convert it into a p-value, which is usually what you'll see in a lot of literature, convert it to a p-value and then compare it with your alpha. So either way works. So Welch's t-test, which I'll kind of skip over this Wikipedia test. For the record, Wikipedia actually has great information on a lot of these statistical, like actually a lot of numerical like formula and definitions and history and stuff like that. So Wikipedia is actually a really great source for this stuff because no one really tries to mess around with it. And even if people mess around with it on Wikipedia, like there are so many people who would get so upset and would immediately change it. Just be aware of this though, it's not perfect. I have come across some cases where something should have been in there and it was incorrect and no one caught it. But anyway, Welch's t-test basically is a modification of a student's t-test. And basically the reason why we use a Welch's t-test is that a t-test actually has assumed same sample sizes. So if you're comparing two samples, for example, they assume that the sample sizes are the same. Technically, you say they're close enough, and also that the variations are the same too. So the variation between two populations have to be the same for students' t-test to work. And basically Welch was like, hey, that's no good. I'm paraphrasing, obviously, but he says, all right, no good. Like, we need to do something else. So basically, I'm going to show you this really scary formula, which is look at it, appreciate it, like, oh, wow, that's really scary. And then don't worry about it anymore. Basically, the main thing you have to know from this is that we're comparing two samples. No, this is x1 bar, x2 bar. This could also be x minus mu, depending if you're talking about a one sample versus a two sample, right? But the idea here is that you're comparing it with, you know, another sample, and then each one has its own standard deviation. So basically what happens here is that, oops, oh my gosh, my mouse is doing weird stuff today. All right. Basically, this creates our new t statistic, and note that it's still called a t statistic, even though it's technically a new test statistic, but it's still a t value, right? And then we also have to compute the new degrees of freedom. So this is where, again, really fun formula, but basically the real reason, the thing to notice it is that the big difference is that instead of having a statistic underneath here, I'm sorry, standard deviation underneath here, you have two standard deviations, one for each sample. And that's the same thing for this degrees of freedom with nu. It's not a V, it's like a fancy V Greek letter, nu. I don't know if you guys know Greek letters, whatever. Anyway, this is like, I think it's actually on here. No? I don't have it on here. No, I did put large V, whatever. Or it should be new. Anyway, so that is your degrees of freedom. And then with the degrees of freedom and your new t value, you can now say, hey, what is the p value? And that basically is the formula that goes through here. And then you got it. You just compare it with your alpha just like normal. So nothing really changes too much. So then you say, okay, how do I actually do this? But yeah, keep it, go ahead.
Could you instead normalize and then standardize your t-distributions instead of using Welch's in order to account for the variance being different and then the mean?
When you say normalize your t-distribution, do you mean like your samples themselves?
Yes.
Yeah, so that's the problem, is that the samples themselves, you can try to normalize it, but then you're saying, oh, we're now going to try to look at across a normal distribution. You're actually changing your data
By using the
versus
central
using.
limit theorem, you're changing. Isn't that where you're always changing your data when you use the central limit theorem? That's
Well, yeah, the reason why the central limit theorem can do that is because of the estimator itself. Is that if we're comparing on the estimator, we can actually sample across the sample to create a new estimator, like the mean, for example, and then use that. But that won't apply necessarily by just trying to change the data and then making a new test for it. So you couldn't necessarily normalize, like, I'm just going to put like normalize your data and then apply a new test on it, because it should still have the same values. Like, it's kind of like saying equivalent, like if I have, sorry, the reason why like we can't just normalize the central limit theorem is because like we're having a distribution that's probably, oh my gosh, my mouse. It's more skinny, but then there's like a normal distribution looks kind of like this. I know I'm not the best drawer. So that's like a normal distribution. The problem is that our sample doesn't actually follow, we don't know for sure if it follows a normal distribution. And so we have to actually use the t-distribution to estimate, say, well, since we don't have that many points, we're using a t-distribution on here. It's kind of equivalent to like if you started off with like about like something that looks like this, like let's say you have a distribution like that, you can't just simply like stretch it out and say, okay, well, we're just going to multiply everything by 5. It's still going to have, like, it's going to go like this, but it's still going to have like this shape, like if that makes sense. So this data doesn't actually change. If we're doing an estimator, we can sample across this part, right? We can sample across this. And then what we'll find with the central limit theorem, we'll actually find this being the means, essentially. Let's say whatever estimator you're doing, it could be standard deviation too. This will actually be a normal distribution. And then each line here is represented by a single sample. And so the reason why, again, like we're not doing this directly to the data, we're actually using this concept to compare it with the t-distribution. So we're saying, well, what if we do it for the sample? And then what if we do it with the t-distribution? Do they look the same? Or say, oh, they actually are very different. So in the end, we're actually comparing two normal distributions. And we're seeing is this one, like let's say this is the one that's formed from the t-distribution, right? Like say, oh, this is a nice, pretty, perfect t-distribution, we can write with a formula. And this is our one from the actual sample from like bootstrapping or something. And we're saying, are these significantly different enough from each other?
Oh, so this has nothing to do with like normal distributions is what you're saying, right?
Right, yeah. And this is where like,
yeah, all right.
Okay.
Completely right, yeah, t-tests are a completely different thing. Yeah, I got you, okay.
Okay, yeah. And that's where like, again, this is why we can actually use a p-value instead of like a t-statistic or whatever statistic we have, or t-critical, is because we actually are doing essentially the central limit theorem to compare two normal distributions.
Yeah.
Yeah. I know, this is where this stuff gets kind of blend all together, right?
Yeah.
Cool. All right, so cool. All right, I think we're going into some code then, right? Yeah. Okay, so let's check this out. So I'm going to use SciPy stats because I don't know, I like SciPy. So we're gonna use SciPy. I'm basically gonna make this little function here. So basically we're gonna compare student Welch's. So I'm gonna compare student's t-test and Welch's t-test with these two distributions, A and B, which I'll create later. To do the t-test for, the t-test for with SciPy, you just do scipy.stats t-test. So here's the actual documentation. And this is where you'll see really quickly like where all this stuff comes from. It says calculate the t-test for the means for two independent scores. This should technically say the student's t-test because t-test is kind of vague in this way, right? And this is where I'm saying like Python stuff isn't as mature. So we basically take in A and B, so two different distributions. We have access, we're gonna ignore that basically if you have like your data is formatted in different ways. And then equal variance. Okay, equal variance is basically for Welch's versus students. So by default, equal variance is set to true, which means we'll actually use a student's t-test. If it's false, we're actually performing a Welch's t-test. So there isn't a new function for Welch's t-test. It's just more like a correction factor, if that makes sense. We just pass this into the t-test index from SciPy. And then also there's some extra stuff that we don't really care about, so we're going to just ignore that part. Okay, and then the end it should return the statistic, so our t-statistic, and then also the p-value, because no one looks at those statistics. We just want to say, okay, what's the p-value, because that's something easy for us to compare. Okay. And so you can see here, basically I have students, Welch's, written out like this. And I'm just going to calculate this for say, okay, like now we should have Welch's and should be statistic and p-value, statistic and p-value for Welch's. And I'm just basically printing these out. So if I run this guy now, you can see these, I'm just basically creating two different distributions. This one has a mean of 7, a standard deviation of 3.5. I'm making 25 of them, 35 of them. So and a scale of 5.5 and a location of 9. So just know that basically that these two right here, oops, I should probably run this guy too.
What does random state do? Because I saw
this guy
that
right
before. Here? Yeah, is that the same as like random seed or something? Yeah, like what is random? Okay.
Yeah, that's right. It's just the seed basically, so we get the same random numbers, which is again weird to say that, but it's so we can be consistent. So if you were to rerun this on your computer, you would get the same exact answer. But if I took out this random state here, then who knows what values you'll get. Like you can get something slightly different. So this just makes it consistent.
So then, okay, just really fast. So that does the number after random state mean anything? Like if I use 27 on mine, would I get the same as yours versus if I put 22, or like how does that, does it matter what number?
If you put 27, it'll be the same thing. If you put 22, then you'll get different numbers.
Got it. Thank you.
We call it the seed because it's like kind of like the starting off point. There's some basically instead of like if you guys I feel like I might be dating myself and like when I did statistics and stuff like this, but if you guys remember doing statistics and like you looked up like a chart and like literally you picked like you read off the numbers to like pick up random numbers. Does this sound familiar at all to anyone? Yeah, no, right? This is what I would do for fun, right? Is like pick up it's literally a book of random numbers and you basically would randomly pick a certain part and you would read off the numbers. That's kind of what's going on here is that it's like, it's not quite the same thing, but it's like almost got a list of a bunch of random numbers and it's picking where it starts off from. It just turns out that the way it does it is that those random numbers also shouldn't cross over. Like they shouldn't like, you shouldn't reach a certain point. And then like, now it's like if you start at 27 and then you do 28, it's not like 27 is like these first few numbers and then starts repeating, or not repeating, but like starts going where 27 is. It's kind of like, oh, it's just a different set of numbers.
Okay, sweet. Thank you.
No problem. Okay, so I run this guy. Oh, I didn't realize what time it is. A little bit late. That's okay. So I run this guy right here, and you can see our t statistics. Our t values. So these are basically from the student's t-tests and the Welch's t-tests. So note that these t values should be different from each other, right, at some level because they are different distributions. However, you can know that they're pretty different here. So I showed the difference as well. So you can see the difference is actually 0.24. So they're both negative in this case. But you can actually see the p-value, which is going to be a big deal. You can see from the student's t-test, we say if you use the alpha of 0.05, we would say this is not significant. But with Welch's test, we would actually say it is significant. So you can see there actually is a real difference between using student's t-tests and Welch's t-tests. Note, however, if I change this up, it's because I selected very specific ones, I put like 30. We should get close. And you can see here, they're both not significant from each other. Okay, so it just kind of depends on like what you have and stuff like this. As we get closer and closer, so let's say do like 30 and 30, we'll see that this value, this difference between the two will get smaller and smaller. So you can see here, very, very small, even though they're slightly different from each other. I'm gonna keep that 9 here, but let's say I do like 3, let's just do 3, you can see this guy will be even smaller. And then if I do the exact same thing, it should be about the same. There you go. But it simplifies to itself because the correction factor, there's no need for it anymore. Okay, cool. All right, I am over technically, which is perfectly fine because then we can talk about ANOVA next time with multiple comparisons. And then that'll lead us into a little bit. So the next part technically is Bayesian statistics. However, I'm debating, I'll let you guys know a little bit ahead of time. Still go through Bayesian statistics. I might even introduce linear regression before that and might even save off Bayesian statistics, to be honest, until like maybe when we're done with, like when we go into project week, because we have a little bit of extra time. But I'll let you guys know because it's not, to be honest, your project will be focused on linear regression. Like it's not going to be Bayesian statistics, but Bayesian statistics does come in play later on. So it is kind of nice to see it. But yeah, I'll let you guys know. If you go, for the record, if you go through section 16, which is Bayesian statistics, if I remember this right, you're not going to be like behind by going through that one first. It's just that I think I might focus more on the study group for linear regression because usually that's where people have more questions on anyway. And it's the thing you're doing for your project. Okay. All right, everyone. Well, I will let you guys go. I guess I probably won't see you guys. I won't see you guys tomorrow necessarily. So if I don't see you guys before in 1-1, have a great weekend, I guess. Of course, just message me on Slack. Oh, also, I know there's a few people here already. I think only Mike and Nadine were the ones who responded. I don't see some stand-ups from some people. I want to know who I need to look out for and how they use their toilet paper. So hopefully it's not too personal. All right, take care, everyone.
Bye. Thank you.
Take it easy. Have a great night.
Thanks, you too.